So let's finish this lecture by saying that we have three types of features: alignment, lexicalize, and text similarity. And so the second strategy, which is really hard, is bridging, because aligned phrases is hard sometimes or impossible sometimes. For example, the predicate is expressed by the light verb have. What government does Chile have? So have could be anything, so that's why we need some bridging in order to remove this ambiguity. And for another example, it is expressed by a highly ambiguous preposition. For example, what actors are in Top Gun, in the film Top Gun? And are could be anything, so maybe we should say play or start or anything. So we should remove this ambiguity by leveraging these aligning phrase by these bridging things. So for example, another example is, what is Italy money? What is the currency of Italy maybe? So maybe currency is something that we should focus. And so this is bridging, and this is the features are log of number of entity pairs that occur with bridging predicate, or the kind of bridging that the binary be injected. And the composition in itself has three feature types. The first feature is rule features. The type of the feature is rule feature. The other one is part of speech features, which is obvious, and also denotation features. And of course, interpretability in AI is very important for me, because I don't want my neural network, which has billions of parameters, just mimics and I don't want it to imitate and copy everything, and like a 2-year-old child who tries to copy words and doesn't understand what people say, just copies them to say that, oh, I'm big enough. Don't look at me like a child. So interpretability of a machine is important. And Richard Feynman says, I would rather have questions that cannot be answered than answers that cannot be questioned. By the way, this is a nice article. I enjoyed it. Grounding natural language instructions to semantic goal representations for abstraction and generalization. Now let's go to this was lecture 15. Now I should talk about lecture 16. Lecture 16 is about Lambda DCS that I promised, because this is the simplification of Lambda calculus. So it is written by Percy Liang, the guy who's very good at question answering, semantic parsing, natural language processing, and those things. So it is beautiful, and is also great for graph databases such as Neo4j by eliminating variables and making existential quantification implicit. Lambda CCS logical forms are generally more compact than those in Lambda calculus. So we have an utterance, people who have lived in Seattle. The logical forms becomes X, there exists some E such that X place lived in E, and it with E has located in Seattle, this is the logical form. So the database retrieves this. All of them are translated to end of SQL or any language or any database, anything that machine understands. So the simplification of that, so the main essence of this article, we can change this logical form, which looks long and difficult, to some simplified, more intrinsic, more heuristic form, which is this: place lived dot location dot Seattle. So it's like a nested things, and it is good because if you have a graph database, place lived could have many things. One of them is location, and location itself could be Seattle, could be Texas, could be some other states. So you see, it's like a graph. It's easier to work on. We've converted these logical things to something meaningful. Because if you look at this graph, whenever I see a graph, I see the beauty of Markov chains. I see the beauty of Markov chain Monte Carlo. I see the beauty of convergence to stationary distribution. So I understand it. But if you give me this, I'm not a machine. I don't appreciate this. Maybe your machine appreciates this. And a knowledge base is, this knowledge graph. We have some entities. We have some properties. For example, from one entity, you go to another entity with some relation. For example, place birth. For example, Farshad, it's me, has a place birth in Tehran, capital of Iran. And unary base case. The simplest Lambda TCS form is single entity. So the simplest things is just unary. But if we go to relations like in knowledge graph, we have place of birth. It connects two entities together. So it becomes a binary case. And we handle that with just dots. And the join, here place of birth is enough. It represents two things. So it's binary. Because it's one entity it connects one entity to another entity. And the third one is join, really appreciated in SQL databases. And the most central operation in Lambda DCS is join. For example, people born in Seattle is represented as place of birth Seattle. So in Lambda DCS, this form is very easy. So you don't need to look at it like this. Lambda x that you see. It is very simplified, and also, as I said, it has meaningful representation in graph theory. And so this is just join is just dot of something. An intersection is just like before. Here is replaced by like this. In Lambda calculus, we write this for and, but in Lambda DCS. In Lambda DCS, we put it like this. This is your and. And same for union. Instead of this, we put it this. So this is simplified. And negation, almost the same. And higher order functions. For example, in Lambda calculus, we say count of these, which is very mouthful, but in Lambda DCS, we just say count of type of US state. You see, it's so beautiful, so meaningful. And then Lambda abstractions. So until now, our Lambda DCS have been limited in two ways. Fundamentally, our logical forms have been tree structured, since the only way different parts of the logical forms cannot concurrently interact is via one implicitly represented overlapping variable. Non-tree structured logical forms are important for handling bound anaphora. And to capture such phenomena, we will introduce a construct called mu abstraction. So this is the mu abstraction. Those who had a child who influenced them in Lambda DCS will rewrite it like this. And finally, I should say, a prevailing theme in Lambda DCS. This is the discussion part of this paper, this paragraph. A prevailing theme in Lambda DCS is that the construction of logical forms centers around sets. Sets are important in set theory in mathematics. But Lambda calculus constructions around truth values. I'm not a robot. So lifting up to sets allows us to eliminate variables, treating them as implicitly consistently quantified. Indeed, looking back to the convergent function, they have the form z lambda x something. Of course, there are logical forms where lambda, this is bad. There are some logical forms where lambda DCS would not offer much saving in reduction of variables. For example, when many predicates operate on the same variables in a non-tree structured manner. However, we have found that for logical forms derived from natural language, especially for querying databases, Lambda DCS is good enough. The way machine understands is like the way my niece understands. This is the conversation between me and my niece. So she's 4 years old. When I say what is the meaning of television, and I anticipate that she says TV is a box that people play. Lots of cartoons and talk with each other, and we hear and see what they do. So, like continual learning, it adds to the complexity in stages. So our basic neural networks here, then when we add lots of, for example, after 1,000 tasks, we have more complex structure, and gradually it develops sophisticated ideas. And another conversation between me and my robot, when I say give me a coffee please, my robot says, coffee is in the kitchen. Kitchen is located in XY. It is enough to reach the dining hall, and the kitchen is next to it. Then I can start the coffee machine and wait for 5 minutes. Then I come back using the reverse of what I've done. Then I will tell Farshad, here is your coffee, dear Farshad. Have a great day. Of course, the robot should say something, but it doesn't say it. It just understands it. That kitchen is a thing that human people have in order to create some food, in order to have a cup of coffee, and those things. But it is not, all of these things, which could be a big paragraph, is done in just 1 second. This is interpretability of AI. So all generalizations, perhaps except this one, are false. So this is a nice motivation for mathematical logic. The father of logic, I think, is Gödel.